Is it working? Uh-huh. Hi. Okay, that's good. Um, so let's talk about the arrangement, right? So basically, we only have 4 classes left. So today we will be doing the finish the repeated game, and then which is topic 6, and then we'll start topic 7. Will be maybe we will done by 13, and then we'll be doing the dynamic games of incomplete information in the last 2 weeks. Okay, and 27 we will have a half class because half the class will be for exam. Okay, the exam is just 1 hour, so we will be we should be able to cover everything we're supposed to cover, but we can't cover any extended material. So basically, it's basic microeconomic theory and also game theory, but really can't go properly up to chapter 8 only. And I guess because chapter 8 is something we can't finish properly, I would not put in the exam. So basically, it's the exam will be chapter 1 to chapter 7. Chapter 8, dynamic games of incomplete information is it's most interesting, but I don't want it. I just teach and then you have to take the exam. That would be possibly not the best fit, but best case scenario. And probably, of course, you probably still want to exercise on that. But I guess I would give the optional exercise on that one. I mean, you can do it if you want to do it, but I guess optional is better because I know you guys are very busy with many things. So just not to want to add more burden on your existing very heavy workload, right? I mean, so let's start. So today we cut the break a little bit shorter because I want the tutorial to be done at the very last 15 minutes. Okay, maybe I cut the break to be like 10 minutes or so that the class will officially end at like 12, and then tutorial will come. Okay, so to make sure if you want to attend, you can still don't go over the time. So let's continue our journey on dynamic games complete information. And just a gentle reminder of how to solve this type of problem. If the game ends in some finite period, you will always do barrel induction. That's easiest, right? So always go to the last subgame, solve for Nash equilibrium, plug that in, and solve it backwardly. And of course, the problem, the complication, it will be if you have more than one equilibrium, then you have to do mix and match. So that would be the point. And the key point to remember is you have to solve for every tree, even though actually it's not right in equilibrium. Okay, the off equilibrium path have to be specified. So I mean, I spare you with the formality, but say, I guess at least it would be good to go over how you solve this game, right? So how you do it is you look at the last game and see if the incumbent want to do what, right? And then in this case, he compare -1 and 1, and the 1 would be the thing he choose, right? And after this, you take this as outcome of this subgame, and you compare for entrant 0 or 1, and then that means he will choose this one, right? 1 better than 0, so that is the outcome. So just make sure that you know how to solve this type of game, and that would be the ideal point, right? And this is definition of subgame perfect equilibrium. And this is how you count how many subgames you are, and then that will be important. So this is simultaneous move is something like more often, right? Because people in different time probably move together. So most common form you will see in business journals will be agents move in sequence, right? Say maybe the supply chain idea would be the manufacturer, more than one, right? Manufacturers are moving at the same time. They decide maybe the price of raw material, right? And then the middle guy, maybe the wholesalers, right? And they all move together to buy stuff and combine things, repackaging, and determine the wholesale prices. And once the retailers see the wholesale prices, they decide the retail prices, right? And the consumer may decide the end, right? So things take in sequence, right? Just like, or you can imagine a setting of a startup, right? The entrepreneur come up with the idea, he can pursue a risky project or not so risky project. And after he decide the project, and then he would get the loan from the bank, and the multiple bank may be competing for his projects, right? Setting different interest rate. And then the entrepreneur would pick maybe one of the creditors, right? And then do the job, and then he compete with other firms. And once he did it, and then make the profit, and then decide whether have enough money to pay back the loan or he simply go bankrupt. So that's many of the model is following this as a style, right? Although it's confirmation, it still allow nature move, right? The nature will decide whether the risky project is going to what kind of return it's going to get. Right? So this is I would say most of the model, if you want to build in business, would satisfy this idea, right? Because unless you think information asymmetry is something important we should cover today, otherwise, this is the model that actually you end up with, and this is very important. Of course, I would say finance, accounting, information asymmetry is important, right? But you need not need the asymmetry, right? Because the information will arrive later, right? By the nature, right? And then you can also model it that way, right? Unless you say the information asymmetry is important, there's a strategic reason people doing that. Otherwise, there's no too much different from what we are thinking. So we have went over the stakeholder equilibrium, which is also, if you talk to people who learn how firms compete, then you probably would know it's Connor, Bertrand, and Stackelberg, right? One is hoteling as well, but that would be the famous model that people using, right? So, or sometimes you have the Salem model, we say circular model, but these are the model that people use to build up their models, right? I guess that would be things you would learn how to solve it. And after that, we learn with the game, and in particular, usually we focus on infinite with game rather than finite one, and because it is not natural to think about their deadline in many cases. Of course, in business application, there may be cases that hard deadline, but it's very likely that they may renegotiate. Right? You know, there are a lot of contract end date, but very likely that you are able to renew the contract, right? Unless there's a hard constraint that you can't really renew. Otherwise, it's always you have to renew, right? Because what the case you can't renew, like in accounting, there's a mandate rotation of auditor, right? So you have to work with this auditor for a few years, then you have to rotate, right? In that case, you do have a finite repeat game, right? But in many cases in business, then it's unlikely that you would have a finite period. An infinite repeat game will be the thing that would model how people collaborate. And we went over this example, which is also a famous example, even in literature, right? People will focus on this with the game, where it's always dominant solvable, and it's always dominant structure defect, but it is Pareto inferior. The problem is how to collaborate, right? And we have shown you that the way to do it is trigger strategy, right? It's like if it has been done in the way that people collaborate, they collaborate. And to support this, as long as people are not so short-sighted, okay, they would prefer 4 forever rather than 5 and 1 forever, then that would be the solution, right? So that's not something very difficult to see, right? The short-term gain is not, as long as people are patient, the short-term gain is not enough to cover the long-run losses, right? So that would be the idea. And of course, in the world, right, we would still see the effect is because we are not patient enough, right? So that is possible, right? And then a gentle reminder of this problem is I need to check how to check Nash equilibrium and how it's different from subgame perfect equilibrium. For Nash equilibrium, you need to check along the equilibrium path, okay, is that deviation, right? The equilibrium path is everyone collaborate. You just check along the collaboration, would they want to not follow the equilibrium, okay? And what is new in the subgame perfect is to check off equilibrium. So what's off equilibrium is if it have not been CC, right? That is the idea, right? So that's the new thing here, right? It's the new thing that because subgame perfect is to check every subgame, right? So we on the equilibrium, you already check this one already checked from the Nash equilibrium, right? This and that. So this is new. What is need to check here is if it's not in the CC in the past, so what have to be done? But if you do Grim trigger, means that Nash equilibrium forever. So this is done, right? So this is automatically done because you are going back to Nash equilibrium. And by construction, this is done. Okay. And in the case, if you do not do Nash, right? As we studied at the end of the last class, is if you are penal code, right? Need not be Nash equilibrium, right? You need to check carefully how we do that. Okay. And here is another example, but we don't have time to go over, but it's a very interesting example. Is even the finite of the game, okay? And you have multiple equilibrium in the stage game, you can support something Pareto superior, but actually it's not a Nash equilibrium on its own. Okay, so that means that it's more interesting if you allow the game to repeat, even its finite repeated, as long as you have 2 equilibrium, you can support something actually is not in the Nash. Okay, so simply that you are now people interact over time. Okay, then actually it's better, right? So one moral of this story is why you need to get married. Why you don't say every life is finite, right? No one live forever, right? So in that case, right, we have personal dynamic, right? With defect, right? Why you have to get married? One reason like this, right? You are signing you're going to interact for more than one period, right? Then you have a carrot or stick, right? In the last period. And in that case, in the first period, you can sustain something very nice, right? And what's this? Honeymoon or first 7 years of your marriage, right? You get very nice outcome, right? With non-Nash equilibrium, right? But indeed, it's Pareto efficient, right? And people said, well, the man has changed or the woman has changed. Well, may not be. Maybe just because of in the first period, you can support something very nice, right? At the very end, then probably people go into more rational outcome. Okay, so probably makes sense, right? Why we have to do something a little bit long run rather than something more short run. I hope that's clear to you why sometimes we want to have a longer run contract rather than short-term contract, right? So here we talk about the repeated game. And as we said, we focus on infinite repeated game. And because finite repeated game by itself is very interesting, right? But it really depends on how many periods you repeat, and then the dynamics is more complicated, right? So that's why we focus on infinite. And also because we don't really want a deadline at the end. So, but recent literature do talk more about the finite repeated game because actually it's more complicated, okay? Because of how the things grow through the time, it's actually more complicated. So that's why we talk about the finite repeated games these days, at least in the introduction level, okay? And not going to bother you with the details, but the key thing I want to say is the this one period division principle, okay? You just need to check for every subgame or any stage, any history, and you just need to think about deviation in that current stage. And after that, you go back to the original one, okay? And that is something that is always no problem as long as you think about your payoff with discount, okay? And that shouldn't be a big problem in your application. So most application, this one would apply without any further codification. So that should be, you can just apply this, and this is a result. If you find out the game, and then if the only stage game has only one equilibrium, that's only thing you would get is finite. The game is just say keep the same outcome. And this Fock theorem actually tells you a very interesting result is once you deviate from finite repeated to infinite repeated, and then that means that you would throw up the set of equilibrium, right, from one element, right, to infinite many, right? So that means that the power of possible future actually change a lot, right? So it's a lot of possibility, right? Actually, that means what, right? Economists are very positive, right? It's not the simple science, what people claim, right? And it tells you that if you are hopeful, there's a future, there's always infinite possibility, right? Right? And of course, that is actually, some people consider this a negative result, okay? Because it means that you lose predicting power, right? Because you used to be, say, if the stage game process dynamic is very precise, we can predict the effect every single subgame. But here we will say, oh my God, then everything can be done, then what are you predicting? Okay. That means that actually when we extend the model to infinite game, then actually we need to introduce something else to shrink the equilibrium. Okay. So that's why we talk about today later, we talk about imperfect monitoring. You don't actually know, or you are not 100% sure what the other guy have done. Okay. Here is I observe what have been done, right? But there may be some cases you can't fully observe, except in business cases. And later you will see how this would make collaboration a little bit more difficult, right? Because here it seems to suggest if people are patient, then they can do a lot of good things, right? But that doesn't really fit very well about our real world, right? Because people actually tend to think very long run, but at least in the modern society, right? But there's still a lot of short-sightedness we can see these days, right? And this is the model that we go for a very interesting model. With the game of Carnot duopoly. And it's easy to characterize whether the scarf is large enough, you can do Carnot equilibrium as the punishment, and they would collude to share the monopoly profit, which is the highest they can get. Okay, and as long as more than that, you're done, right? I think this example actually very interesting. Tell you that how you can do when it is not patient, right? It's something that you don't learn in the hopeful. Usually, you don't learn in the undergrad, even you have studied the game. Okay, this is something PhD level material, right? Because you would have to be very careful what they can do, right? The best case and what they would defect under that case, right? And that would be a slightly more complicated, and that's the result, right? You will see that if they're not so patient, they cannot trust each other that much. So they have to collaborate at a lower level, right? They can't collaborate at such a deep trust. Okay, so they remain somewhat a competition and some collaboration. Okay, so that is the idea behind, right? Because this is fully trust is there, right? They can split, but here is they can't, right? This is the worst case. They competing, right? So say somewhere the red one represents some collaboration, but some competition as well. Okay? And so that's the idea, right? So there's no full trust, but there's not full distrust. Okay? So here you see that the green one is the Carnot model, and they're able to go to the blue one, but the red represents something, the red line here. Okay, so it depends on how the delta changes, you will move from this one, right? If you decrease the delta, you decrease to here, right? To the green one. So that would be the reason that I color the model in that way. And the technical part would be here we don't want to go to detail, but telling you that it need not do the next reversion, right? Because it just simplify our checking of the subgame perfect, but it's not really ideal, right? Because of the next reversion is this one, right? Go back to the M. Okay, you want to support this guy, but whenever D, we go to the M, right? But M is not the worst case scenario. You can punish the other guy, right? So M is basically you punish the other guy, but you also punish yourself. Right? So that's why the Blue actually come up with the way that you very carefully that you design a punishment to each agent such that if anyone would deviate, would have to follow his punishment. So basically, you say instead of punishing the same, go to next for everyone, you would have designed specific punishment for each one. Okay, not together jointly punish, but you would be punishing. If player one deviate, you go to this one. If player two deviate, you go to A2, right? And along the path, if any player deviate, then you will also restart the punishment again. Okay. And in that case, actually, you allow people actually not so patient also can support the better outcome, right? Just imagine this is a carrot and stick, right? And here is that you allow the stick, it's not same for everyone, right? It's especially designed for everyone. Then that would allow actually lower disagreement point. And that actually can generalize into a general idea, turn out to be, we can extend the Fogg theorem, okay? Such a way that you will, as thought the outcome is strictly bigger than this mean max outcome. My mean max outcome is, this is the punishment all other agent can punish you, right? Because if the other guys you deviate, then everyone can collude to punish you, right? So this is the penal code, right? That the worst case is this one, right? Because I can make sure that you would only get this one, right? Because everyone jointly work against you, right? And this is the best thing you can do if you are against the world, all right? So as long as this is the restoration level, then they can support, right? Because if you're naughty, everyone try to punish you. Okay? The worst you can, right? So as long as you're patient, then I can always punish you without any problem because I look at the very long future, right? So one period deviate doesn't really matter. So that would be the model. Of course, this model again is super negative, right? Because of what does that mean? It doesn't mean anything can be equilibrium almost, right? If people are patient enough, right? Of course, the question probably would be, as we can see, what happens if this delta is small, okay? And this is something still very difficult to do, okay? But if you want to work on it, there's something can be done. But as far as I understand, this is something in general is not easy to do. Okay? When delta is small, how to characterize the equilibrium, something is very difficult. But that means that if you want to do a bigger game in a paper, you have to show what happened when delta is less than 1, right? Because everyone knows when delta go to 1, then you can support everything. Okay? The job for you, if you want to write with the game, will be solving the model when delta is small. Okay? At least not go to 1, right? No, go to 1 we know very well. So now in the last set of slides, I want to talk about what we call application. As a business school, probably we want to focus on how firms compete. As application, that's what we call price coordination. That the two-type model. One is called perfect monitoring, which is the standard. And the other one is called imperfect monitoring. It's also standard, but we look at the case where you're not able to perfectly observe what other may have done because it may be polluted by some noise. Okay, you see. Okay, so this is a famous paper, and the famous is an AER, and then it gives you some counterintuitive idea. Okay, you will see very soon, and also very interesting as well. So in this model, okay, the consumer's demand can be high or low. Okay, and you can imagine this is a more like macro style model. When the economy is good, people like to buy more, it's QH. And if they are not, then it's QL. So remember, we're still in this phase of complete formation. So that's why at the beginning of period, we know this, okay? And remember, consumer is not really strategic in this model. So just buy or not buy based on the prices, okay? And his willingness to pay is 1, okay? As long as the price is below 1, he'll buy, okay? Of course, he will go to the one who may offer cheapest, of course. And the nature decide whether it is good or not, okay? W may be the probability of good outcome, and 1 minus W is the bad, okay? So it's nature decide whether the economy is good or bad, okay? And it's severely uncorrelated, so different point in time, it's unrelated. So if I tell you today is high, tomorrow can be high or low with the same probability, okay? Telling you today doesn't tell you tomorrow. So it's like, it's more like a random walk, right? The random walk of the demand side, okay? So we can't really predict well about the future, okay? And you can easily check that this is not crucial. You can change the model, allow some serial correlation. It doesn't really matter, but just to simplify the math, okay? So How does the firm compete? It's very simple. There's two firms there. They compete in per chart. So it's easiest you can think, right? Because the per chart means that if you are lower than the other, you got the whole market, right? If you're higher, you get zero. So here is the, if you're higher than others, you get zero profit. If you're same as other, you split the market, right? And QT will be the quantity, right? Quantity can be high or low, right? Of course, I assume the price is less than one, right? Of course, if the price more than one, then no one will buy anyway. Okay. And if you're lower than the others, then you get the whole market. Okay. So that will be the model. Very simple, standard Carnot. Okay. And since it's the game, so it's good to look at history. History will depend on what has been the demand in the past, high or low. But basically, this is useless, more or less, right? Because it's independent and there's a price there. And what should be the strategy? It depends on history, right? And also depends on what is this period market demand, high or low. Okay. And then the firm will decide price. Okay. Of course, price is from 0 to 1 to be reasonable, right? Because charging more than 1 is not be doing anything good. Okay. So, of course, we know for theorem, it means what? Everything will be equilibrium, right? But we want to look at some interesting equilibrium. Okay? And this interesting equilibrium with the following. Okay? Not surprisingly, this price will be based on your demand curve, right? Okay. And this what we say is if people are patient, okay, they will charge one forever. That means that this is nothing new but what? For theorem, right? Regardless of the outcome, right? They just charge one because people want to pay for one, right? They collude, right? There's a monopoly outcome, right? There's nothing new. This is a standard for theorem. And then if the firm are not patient enough, what happened? Just per chart outcome, right? So they can't look at the future. So they do, per chart go to 0, right? So that is very nice two extreme cases, right? The first case would be if they can collude, they collude to 1, right? If they can't wait tomorrow, they just compete to death per chart outcome, okay? So what's interesting, as I said, right, is somewhere in the middle, right? Same as the Carnot case, remember, right? One case is they can collude, the other is not, right? Okay. The interesting case is in the middle. Okay. And in the intermediate discount factor, this is something counterintuitive, and that's why I end up in AER, is they show that, very interestingly, they can collude at the low price. Okay. When the demand is low, they charge monopoly price. When the demand is high, in fact, the price is lower. Okay. So that is very interesting because if you ever learn macro, it doesn't make sense at all. It means what? When economy is good, the price is low. When economy is bad, the price is high. Okay. So that, of course, they try to connect themselves to a macro phenomenon, but it's not the reason we talk about. But he did explain that price war do happen when economy is good, right? It's not something too crazy, right? If you remember in the old days, I mean, not so old, but several years ago, right? We will see a lot of price war, right? And that happened because probably it's like the economy is better at that time, right? People are going to spend more money, right? And this delta defined this way, but we'll talk about this very soon. But I hope it's clear what we're talking about, right? So of course, And this is not the only equilibrium, right? But this is one interesting equilibrium that we may consider. Okay, and if we try to draw this, and the green one would be 1, right? Because your patient enough is 1, and not patient is 0. And you will see, as we said, right, if bad economy is like this one, good economy like this one. Okay, and not surprisingly, if you are the delta goes to the delta head, actually go back, it converts to the same one. Okay, so it's pretty interesting because 1/2 is something that split the outcome. Okay, suddenly you come from Bertrand, it jump to something they can collude. Okay, okay. So now maybe good to see why this is true, right? Because we saw this some more surprising. We see why this is the case. Okay. Now let's do the proof and see why this is true. Okay. So we will use what we call the trigger strategy, right? So with natural, right? Because Bertrand, so if anyone deviate from what we propose, you got 0 for effort, right? So we'll go to Bertrand every period. Okay. So that means that this is 0 for effort, right? So if you deviate, you just, the best thing you can do is monopoly for 1 period, right? So it's your deviation at the good time and deviation at bad time is here, right? Remember, you have 2 subgames to check because each period you have good outcome or bad outcome. Okay? You check if you are being a bad guy, right? You just charge epsilon less than that, right? But right, so epsilon price lower than what you propose to do, right? And so this is the case, right? And look at this. If you, this is the gain you are being colluded, right? You collude, you get half of the payoff, right? Half of the market. And in the future, this is what you get. Why? Because in W of time, you will have high output next period, right? And 1 minus W, okay, you have this one. And over 2, because you half of the thing. And because this is continued forever, right? Because every period you will say serial uncorrelated, right? So that's why this is delta over 1 minus delta is this forever, right? Because every period is independent. So this is the future possible payoff, right? If you follow this, what we call one shot deviation principle, just deviate once, okay? And similarly, you can deviate in the bad time. Okay? You want this to happen as well, okay? So that would be what required for these 2 equations, right? You want that in the bad time, you can deviate. In the good time, you can also deviate, right? You want to prevent these 2 deviations. So if you try to solve this one, okay, just make delta the subject, right? You end up in this equation for the first one and second one with this one. So what you will see, the denominator the same, right? For these 2 fractions. What's difference in numerator, right? Okay. So what does that mean? What does that mean? Okay. So let's see the next slide. Okay. So first, you see if delta large, this is true, right? Because if this is like 1 large enough, large more than this thing, then this is true, right? It's not difficult to see, right? This is the fraction 1 plus, and this is must be less than 1, right? The fraction. So your delta is large enough, then you can simultaneously satisfy the two without any issue. Okay. And you can figure out what is the threshold of this by setting the price to 1, because there's the collusion outcome, right? You set this to 1, this to 1, this to 1, this to 1, this to 1. That gives you this, the threshold. Okay, you put this one, put this one, put this one, right? Because when put this one, these two inequality are the same. Okay, so that I explained these 2 bullet points. Okay. So now let's check the first thing, check the denominator. Okay, look at the denominator. Okay, and why is the case we need to have a PL bigger than PH? Why is the case? Why is the case? I think I should check numerator, but anyway, why is the case? We want to have QH as lower and QL is higher. Okay. The reason, of course, for this to support, we really want this thing to be as small as possible, right? And remember, QH is bigger than QL, right? So look at this, is bigger than this guy. So in order to make easy to satisfy, you need to make this one lower, right? The easiest way to satisfy is to make QH lower, right? Because who is going to, the same, who is going to violate first? This guy, right? So the easiest thing to make it work is to lower this guy, okay? Without violating the constraint, okay? So to reduce this one, okay? And you can check, okay? The price is lower, okay? And it would explain, actually, that's the paper KDR is, you have a very high period of high price, okay? And there will be some reason why you have a very price war, right? When this economy is good, okay, that will be a period of price war over there. Is that okay? Is that okay? Okay. And after the break, we talk about this case of imperfect monitoring. Okay. So far in this one, we know exactly what the other guy they're doing because I know the price the other guy charged, right? Because if I have no quantity sold in the current period. Actually, I know the other guy has defected. I can detect immediately the other guy is cheating. Okay, it's an instant detection. Okay, there's no need to detective, right? But the next one, it may not be possible to detect, right? Because if it's not, say, for strong competition, and you might have some also other, you compete in quantity, right? And the price is not immediate, you know the other guy's defected or due to some bad economy, right? You're not actually sure, 100% sure the other guy defect, right? So what you're going to do is you will forgive for some randomly. Okay? Later you will see how we solve this kind of model. For the moment, let's a break of like 12 minutes, right? And we cut the break a little bit shorter because I want to end this we have tutorial a little bit early. So I know that people are busy, so let's make the tutorial at 12. So let's a break of 12 minutes. We will resume at 10:30. So the next thing we want to talk about for the game is again what we call the secret price cut paper. So it's the price cut is not directly detected, or it's same as before. It's also a repeated Bertrand model. And if the two firms produce at zero cost of production, and the world is also good or bad, right? The same as before, it's good with alpha and bad one minus alpha. So the state of the world is not observable. Okay, so that is important. Okay, they don't know actually the world is good or bad. So that is important because I cannot sure that actually I can't sell the good is because of the other guy defect or just the world is bad. So this is the game. As long as the price is below 1, Q is 2, so it's the same as before, right? Just the difference is what is the pay? Just 1, and then the market size is 2, right? So that is nothing deep here. And if you have the lower than the others, you get the 2 of the market, the same, just 1, and then otherwise it's just 0. So just they normalize the quantity only. Okay, that's a good. And the bad case is very simple. Everything is 0. Okay, the bad case, no one need your product, and profit is 0. Okay, so that means that the important part is you can't distinguish this guy and this guy. You can't tell the profit is 0. It's because of the other guy actually being very bad, take away your market by lowering the price secretly, or that is due to actually the world is not favorable. Okay, so that would be the thing that we talk about. So it's not sure due to the bad state or bad price. Why? This is different from classical model because you can't really do the trigger strategy, right? You cannot say, okay, once I saw no price and no profit, then I would just defect, I just punish forever, right? Because it's possible that actually the world is bad. So no matter, even the guy is not defecting, so you can't really say that he's bad, right? So if you punish, then you can't collaborate, right? Because you would for sure in some period of time in the future you punish. So why you would have any chance to collaborate? So that is important. So that is a ideal to break down the fog theorem, right? The fog theorem will tell you, okay, we can collaborate directly, right? So you have to be a little bit more creative in solving this kind of model. So that is in the literature, there will be 2 possible ways at least. The main way to solve this problem is to consider what we call public signal. Of course, there will be some way we call, as you see, the public. That means that there's other literature that focus on private signals, but that would be way more complicated. But so that's why I focus on the simple one. It's called public signal. So what is it? Is they would also observe something that is totally irrelevant. Okay, and this irrelevant signal can help us to collude. Okay, so this is just a uniform number from 0 to 1, can be anything redundant. Okay, this completely redundant thing, and turn out this redundant thing can help us to do stuff. Okay, so you may say this is something crazy, and actually indeed people in the practice do collude based on somewhat more crazy randomized device. Okay, and they do say allow us to collude when the weather is good. Not, then it's not. Okay, there's actually something like that. But anyway, you see the structure. But the fun part is when you have this kind of uniformly distributed irrelevant stuff, completely unrelated to payoff, but that's helpful to do stuff. Okay, so it's a device. So you will see this kind of equilibrium will feature the following thing. Okay, first is, of course, we want to see if they can collude, right? So this is the case where they jointly collude, right? They collude at the price 1. And this punishment is go to Nash, right? Nash, the first one competition, right? So the key thing is this one. The punishment period is finite. So you get punished for a period of time. And there is also a very important feature is what we call the cutoff of the sunspot. So that means that later you see this is the crucial for them to decide what should go into punishment. Okay? Later you see immediately the structure. Okay, the structure like this. At the beginning, the game start, the clue. No problem. If the history has been colluding, okay, right, regardless of what the sunspot, then they collude, right? If we start the collude, if it has been collude, it's still collude, okay? So the key point is number 3, okay? Key point number 3 is if the last period, I don't earn any profit, okay? No collusion. But, okay, this is the profit, okay? The profit is 0 for me, right? But I can't observe the other guy profit, right? I only know my own profit, okay? So this is what history they know, right? And they also look at, okay, if the sunspot, I mean the random event is good, the temperature is nice, okay, then I still collude, okay? So that is the key point here, 1.3 is you will still collude if the public signal tell is good, right? If the weather's nice, although yesterday is a bad day, I still do the right thing, okay? Okay. And 1.4 is not really deep here. It has been saying that, okay, if last T period, okay, has been 0, okay, from next period, we will do good thing. So we have punished for T period, okay, regardless of punishment due to what reason, but there's been 0 for last T period, we forget, okay? Our memory, our bad memory, only keep us for T period, okay? And T period afterward, we'll go back to collusion, okay? So that's a limited memory here. You would, okay, for T period after, you forget, okay? You're forgiving, okay? Otherwise, if you don't forgive, then you end up with punishment forever, okay? So 2.1 is not surprising, right? Because you need that because you have said, if I earn nothing last period, and look at the sky is blue, or no, the sky is great, then I will be bad, okay? The second is trivial. It means that if we're in the punishment, we will keep punishing, okay? Is that okay? So let me repeat. It means the following. If it had been collude, you will collude. If it's bad, okay, just last period, I will forgive, okay, if this is good, okay? But you have been bad, okay, in the last T period, okay, I will do the punishment, okay? So that is the idea. Okay. So now let's look at what is equilibrium payoff, and I will to check whether deviation occur. So this strategy called T beta, because you have to decide what's T and beta, okay, will be characterized the following, okay? If you follow the equilibrium, okay, you have 1 alpha, the chance is good outcome, right? And 1 minus alpha, you get bad economy, get 0 anyway, okay? So you follow this, you get good outcome, okay? And what happened to next period? Next period, you get good outcome. Okay. But if you bad outcome, if the sky is bright, you continue to be good, right? You said good price, you are not bad guy. Okay. And in this case, you continue to collude in the next round. Okay. This is this round, and next round you still collude. Okay. And but if unlucky case is if the sky is not bright, that means that we will be in the bad mood, right? It's fighting for T period. And you solve this equation, end up in this formula here. Okay. Is that okay? Just put VT beta on the left-hand side, right? So just solve this out. So what we want to have is, and this outcome must be better than your DVA, right? We just check one short deviation, right? Suppose you're being naughty, right? You set the price high enough, right? And if good economy, you get 2 because you grab the whole market, right? But in the case of bad economy, actually you don't get anything, you get 0, right? But since you have been a bad guy, right? So you will be forgiven if the sky is bright, which occur at 1 minus beta. So we go back to collude, right? Because you just, it's not detected, okay? But if detected, you actually go to bad case, right? So once you solve this out, it's like this, okay? So what you want is to compare these two expressions, okay? And compare these two expressions. And you combine, right? Just basically solve this out, okay? And combine, you would say this kind of equilibrium would exist if this is true, right? So just look at this inequality. You see when alpha is small, which is bad economy is not likely, then you can easily support collusion, which is not something surprising, but it's easy to see, right? This is the first thing. The second, okay, is you want to further pin down this, okay, and turn out that this is just this guy. Okay, I will spare you the proof, but it simply means that, okay, when alpha is small, you can support, okay, and when delta is larger, all right, that means that this is more likely to be bigger, right? Because it's directly proportional to delta on the right-hand side, right? So I'm not going to talk about the proof, but you can easily check because I think your math is good enough. But anyway, but what does that mean? It means that you can collude if people are patient, which is not something you would worry, right? And when it is alpha, right, cannot be more than 1/2, all right? Because the best case scenario, delta equal to 1, right? If your bad case is more common than good case, then this kind of equilibrium cannot be supported. Okay. But at least what this model shows, very interestingly, is you can explain why you have some period of collusion and some period of price war, right? Because price war will be exist for T period, okay? And they will be stable and compete and stable and compete, right? So that would actually give you a nice model to say, even if a firm they collude, you will see price war, right? It's not something like they collude forever, but the price war is necessary to sustain a collaboration, right? Because that means that actually, when you regulate or when you look at the market, the existence of price war is not implying they can't collude. In fact, the price war simply reflects, okay, how uncertainty the market is, right? How likely they can observe the other, right? If they can't really observe the other people actions, then you would have longer price war. Okay. So I hope that explain a little bit more, right? And you will see how the alpha change to T, right? If you have alpha is more, then you have a longer T, right? You have longer T, but that would be something that you can think carefully how to work this out. Okay, but I think this is an interesting model because this is the classical paper that talk about when you can't observe others. And as I said, there's a whole textbook talk about with the game. Okay, and they will relax this kind of idea if there's no such a sunspot, right? There's no public signal, then what can be done there? Okay, there's some way to do it, but there would be, you can see this paper is already pretty new, only 10 days ago, 30 days ago. So the reason would be also along that line as well. Okay, is there any question? Of course, you will see this two application is a little bit more math demanding, okay? But I just want to show you what you may see, because video game is actually a technical subject, so I can't really skip too much, okay? But you're welcome to read the original paper if you find something I didn't explain very clearly enough. Reading original paper is always good to go, okay? Okay. If there's no question, then I would continue on this one. Okay. Is there any question? I mean, of course, probably I would just do introduction and a short break, right? Because I think that would be a little bit too much to continue too further. But I would try to talk about what is the static Bayesian game. Okay. So actually, before the 60s, actually economists, some of them argue that game theory is not useful because the common knowledge assumption is very strong. What's common knowledge is everybody know how the games works. I'm sure that how it works, and you know it works, and I know you know how it works, and you know I know how it works, and so on and so forth, right? That is a very deep assumption, and it know every single details without any problem, right? And in the real world, is everyone keeps some private information, right? It's not everything is transparent. Actually, I may not know your payoff is 5 or 5.6, right? Because it's not unclear, okay? And in many cases, this information is very crucial, right? And if I don't know the information you have, right? How can I choose, right? How can I say, what I do? Because our payoff are independent, right? If I don't know, there's no way to proceed, right? So that's why the game of incomplete information doesn't work, right? Because if you don't know, then what can be done, right? Just like regression, right? I mean, if you don't have data, then how can you run regression? Right? Of course, you can do some imputation, but you have to come up with some idea, right? So that's why Hasse, I mean, of course, he got the Nobel Prize because of this. Is one of the reasons is he introduced what we call imperfect information instead of incomplete. Okay, it's very similar to the way we model uncertainty, right? Is we will say, okay, players, they all have their own private information. Okay, they know what they can do, they know what's the payoff, they have their own set of actions that can be done. Okay, but okay, every player can form a subjective probability, form a belief in what other people might have, right? I don't know whether you think this product is valuable to you or not. Okay, but I can say I don't know your value to that, but I would say I would assign probably 1/2 that you think is good, to put a high value, and you have 1/2 you think is low value. Okay, so you would, if you're willing to make this assumption, okay, instead of I don't know what you like, okay, but instead I say maybe half of time you like to eat Western food, half of time you like Chinese food. That's okay, right? Instead of saying I don't know what you don't like, right? Where we go to lunch, that's difficult, right? But rather than that, I make some assumption over that. Of course, that will require you how you can find this belief, but let's assume something, we can proceed, right? So that's the way, right? And in many cases, you can make those assumptions, right? But of course, this assumption, is it right, is an issue. But if you're able to make those assumptions, we can solve the game, okay? As long as the solution doesn't depend too much on the structure of the subjective probability you assume, then you get some general conclusion. But if your conclusion really depends on the structure of the belief, then of course people will complain. Okay? And that is, if you look at mechanism design literature, there will actually people complain because the mechanism is highly depend on the information structure of the agent. And that's why recent 5 to 10 years talk about the robust mechanism design is trying to avoid this problem. You try to code for many more cases. It's less information assumption, okay? But at this stage, we'll make this assumption, and this is very common in all the business model, okay? So let's see, okay? And here is the key is the nature to design what private information a player may have. So that's the thing is, in this model, you can imagine it's a dynamic in the sense that the nature decides which kind of player will pick. Okay, you'll be player we have high value, or the player like the Chinese food, a player like the Japanese food. Okay, the nature will decide what it does, depend on actually who they are. Okay, so that means that we can consider what we call the Bayesian game is okay the following. Okay, so it's same as before. We have player set, strategy set, and payoff function. Okay, and some player or all player, or at least some were private information, and private information will be affect their payoff. Okay, okay, and we use type to represent this private information. Good. Here's type 1, type 2, type 3, type n. So it's generic. Okay, of course, type can be continuous as well, but then there also some complication when you go from static type and to continuous type, but we just ignore this technicality here. And here, why is the Bayesian? Because everyone have, before the nature draw, people have the belief over others. Okay, but once you have drawn, okay, and you update based on that, that's why Bayesian, because our type can be dependent, right? Because today may be hot, we would like some cold food, right? If today is cold, we may like some hot pot, right? So that can be related, right? So it's just like auction, right? I would like the object more, and it is very likely the case you also like the object more, right? Because you imagine it's like we're looking for a right for pumped oil, right? If I think it's valuable to me and also should be valuable to you because we are going to sell the oil to the market anyway, right? So we'll stop here after we have a break. Okay, is this maybe after this first line? Okay, because it's good to continue. Okay, so we'll start what we call the common belief assumption. So before the nature draws, every player would agree what kind of type we realize, right? Maybe I like Chinese food, you like Western food, okay? With some probability, okay? Everyone would agree what might be the information that you and I have, okay? So there is still within the common belief assumption. If we drop that, then things will be very ugly, but this is something everyone adopt this, okay? That is called the common belief, okay? Everyone will share the belief on what is the joint distribution of types. Okay? It's types of everyone, okay? And where base rule means that once I know my type, I look at other people's type and form a belief, okay? And this is useful only if our type are related, right? In many cases, in fact, is the type agent joint is independent, right? So maybe I like Chinese food depends on probability 1/2, right? Roll dice. And you also roll dice, but our dice are independent. Okay. In this case, it's trivial satisfied, right? Because this is same as original, right? This is common belief. It's only meaningful if our information our types are related in some sense. Eh? Suppose it's a case that if I like more Chinese food, related to the case you like more Chinese food, right? Why is the case? Maybe we're traveling to some random places, right? And if we're in China, probably we do this. In a Western country, then we'll do Western, right? Or it may be due to the weather, right? If the weather is good, we like Chinese food. If the weather is bad, we like Western food, right? Together, right? So that would be the idea, okay? But that means that it's not independent or dependent. So this means that how it updates. So that's why the base rule. So here is the definition of the Bayesian game. It's the following. So N is nothing new, right? Number of players. S, nothing new. The strategy. U, nothing new. Payoff. All right? So what's new here is what we said, the two things. And is the type and the belief. Okay? Type is what player can do, right? Can have is the type. Can be different payoff, can be different action. But we are being lazy, so we just basically the strategy with the so the type just profit information just affect your payoff. Okay, so that is only thing the type would do. Okay, but in this particular model, we just focus on type. Okay, would affect your payoff. You can remember type is different cost in cannot monopoly, right? And belief, as I said, is based on the others. What is this? And usually this doesn't really change according to our own many cases. Okay? It's independently generated in many applications. So it's not related. Okay, and that become very simple, right? Usually you make this assumption. Of course, you need not do it, right? But this is something we often do it to simplify our model, right? Because if my type my belief depend of your type depend on my type, then you need a more elaborate model. Okay, it's okay to do it, but in this application, that usually is not, except some option, is not. There's something related. Okay, so just to remind you, once is your payoff depend on your type. Okay, and second is your strategy. Okay, is no longer the set of action. Rather, is your type mapped to each action. So it's very important is for each possible type, you tell me the action. Okay, so that is the idea actually subgame perfect because the nature move first. You can imagine Okay, nature move first. Nature pick a type of U, you need to make a decision, right? But you have to specify all possible types what might be done. Okay? Because imagine the nature